can we do 7.3?
Okay. Yes. Well, first of all, I apologize. I should have the test graded by now. And I'm most of the way through. Well, about halfway through. And that's, yeah, I should have it graded by now. So I'm sorry about that. I know it's stressful for you guys. I know it is. Because I don't, not knowing how you did. I know. No. That's because, well, I always was desperate to get a test back that I did well on. Because I was so, yeah, and then I never even, I was a bad student and I never looked at the tests I did poorly on because they were too painful for me to look at. Those are the most important ones to look at and see what you did wrong. But I had a hard time dealing with that. So. It is what it is. Yeah. So what was it, 7.3? Okay. Okay. So we'll go over this homework problem. Finish up simple harmonic motion, just do the pendulum today. And then I'll go over the test if you want. You can see how you did on the problems, at least. And maybe it'll be less distracting. Maybe this is just a lesson thing and you'll be less distracting so you know your grade as we go over the test and you can pay attention. Maybe, I don't know. Either sometimes it works that way, sometimes it doesn't. All right, during the earthquake, so this is problem 7.3. During an earthquake, a skyscraper is designed to sway back and forth with simple harmonic motion in a period of 8 seconds. 8 seconds, I'm going to draw a picture of what I imagine this is looking like. So I have a skyscraper back and forth with a period like that, or something like that. Okay? The amplitude at the top floor for a particular earthquake is 70 centimeters. I'm going to draw it up. So it moves 70 centimeters in each direction.
So is that the same as the radius then? The whole circle?
No, this would be the size of the motion at the top. I'm imagining the top's like a mass on a spring, going back and forth like that. Okay. Okay. With respect to the simple harmonic motion of the top floor, calculate the following quantities. The radius of the circle used to represent simple harmonic motion. Well, yes, that would be, so you're right on that one.
Okay.
So I imagine the top floor is like, if I just imagine that, it's I can think of it as a mass on a spring. Okay, and then the spring goes back and forth with an amplitude. So that means if this is its equilibrium position, its maximum position is here, its minimum position is here, and this is 70 centimeters. So if you recall, for simple harmonic motion, we could think of this mass on this spring going back and forth as like the x position of a point on the edge of a circle that's spinning. So if I have a spinning circle like this, let's say I look at it from the side, I look at the edge of it, the edge of it, this edge goes back and forth. This is in center position, and this thing would appear to be going back and forth. The distance from the center position would be the radius. And so, you know, and this can be, in the x position here can be used to represent simple harmonic motion. So, this 70 centimeters would correspond to the radius of that circle, right?
Mm-hmm.
So A, R equals 70 centimeters, or 0.7 meters.
Mm-hmm.
be the speed of the object moving around the circle. Oh. Okay. So how would we get this?
Potential energy and kinetic energy.
Well, here we know that the period of motion is 8 seconds, right? So it takes 8 seconds for this mass to go back, forth, and then back to its original position. So that would correspond to 8 seconds to go all the way around the circle, right? Okay.
So we can do acceleration.
Yeah.
If the whole amplitude is 70 centimeters, shouldn't the radius be half of it?
It's not the whole.
Amplitude.
Oh, it's just
So
this
the
way.
amplitude is 70 centimeters in one direction and 70 centimeters in the other direction. It's what's in front of the sine or cosine of omega t.
So technically, you just find the circumference of the circle, right?
What's that?
You just find the circumference of the circle, right?
Divide by 8 seconds,
Yeah,
and that gives you the
period.
speed. Yeah, that's right. Because if this corresponds to mass going around the circle in 8 seconds. So if we know the radius of the circle, we know how far it traveled at that time. Distance divided by time, speed. So we get that 2 pi r divided by 8 seconds is equal to v. Okay. It says c, the angular velocity. Well, omega is v over r, right?
Mm-hmm.
The angular velocity. And that should be the same thing as 2 pi over the period here.
Mm-hmm.
And then the maximum speed of the top floor, where would this be moving at its fastest?
Not the edges in the middle.
Edges, it's turning around, right?
Slow,
At the edges. So where would it be going its fastest?
In the middle.
In the middle, yeah, that's where it's going its fastest. This is where you want to use potential energy. So, what do you know about omega, the relation between omega and the spring constant? Mass. Do we know anything that in simple harmonic motion how this is related to spring constant and mass?
Oh yeah, omega is a square root of k over m.
Yeah, that's important. So I'm going to put a k here and just call this top floor having a mass m. I don't know what it is. I'm hoping that as I do this, I won't have to know what it is because it doesn't tell you. So, for a simple harmonic motion, mass on the spring, omega square root of the effective of the spring constant over the mass. Okay, and the energy, potential energy is 1/2 k times the distance it's stretched from its equilibrium point. Yeah, we can call that d squared, and then as potential energy, kinetic energy is 1/2 m v squared. So if it's at its furthest point from equilibrium is 70 centimeters, what's its v?
Zero.
It's turning around. Does it have any v?
Mm-mm.
Yeah, no. So if it had, as it's going over there, it stops at that point. So that means that the total energy, which is potential energy plus kinetic energy, if it would be 1/2 k times the amplitude squared.
But I thought you said that we were calculating the max speed and that's at the middle, so why is v 0 at that point?
Well, this is at the amplitude. This is at the maximum
max.
displacement. I'm trying to figure out the total energy here.
Okay.
And then I'm going to go and look at, when it's going through its center, it doesn't have any kinetic energy. It doesn't have any potential energy when it goes through its center. So So I know all its energy as it's going through its center will be kinetic energy. I can get V then. But I know that its total energy will be this, because at its furthest point, that's when it's at the displacement's the amplitude. It'll have maximum kinetic or maximum potential energy and no kinetic energy. Does that make some sense here? That's the 70 centimeters. Okay, so that would mean that 1/2 A squared is the total energy. That has to equal 1/2 kb squared plus 1/2 mv squared at any given point, right? So if it's going through the center, what's the d, the displacement from equilibrium?
7.
So if it's going
Oh,
through
0,
the
0.
equilibrium position, yeah, 0, right? It's 1/2 mv squared at equilibrium position. And this would correspond to where the V is the biggest, because the potential energy is minimum there. All right, so I have this stuff here. So I have 1/2 K A squared is equal to 1/2 mv squared. I'm going to get rid of that 1/2, dividing that through by on each side. Remember, I don't know what K or M are. But notice this, I can divide both sides by M. So I get K over M, A squared is V squared. And I can take the square root. So square root of K over M, A is equal to V. Now what was that square root of K over M again?
Omega.
That's omega. So I could put this as 2 pi over T, same thing as omega. A, amplitude is. That's a good problem. See if you can make sure that you understand it all and work through it. There's a lot of physics in that problem and it's not hard calculations. But there's a lot of kind of weaving your way through it and working in that physical morass. Good. One more thing I'd like to do and then we'll go over the test. Does this make sense to everyone?
Just erased it or something like
I really like that problem. I'm going to make sure I write it down.
Okay, that's so crazy. You're going to put it on the top side.
No, I just really like it.
Yeah.
Okay. So, simple harmonic motion. So we've dealt with mass on the spring, right? There are many other things in nature that actually behave similarly to simple harmonic motion. And I'd like to indicate why really quickly. This won't take very long. This is a little bit tricky, but hopefully we can make some sense out of it. You remember that potential energy is 1/2 K d squared for a spring, where d is the displacement from equilibrium. If I were to plot this, I'd have with potential energy on the vertical axis and d on the horizontal axis. What type of shape would this be? Anyone know? It goes like d squared.
Oh, parabola.
So it would be a parabola, right?
Mhm.
Something like this. We know that the total energy of the object of a mass on a spring is equal to the kinetic energy plus the potential energy, and that is a constant, because this is a conservative force. So if I put total energy, say something like this, then the kinetic energy would have to look something like this, so that the sum of so at any given point, the sum of the potential energy plus the kinetic energy would equal, well, maybe, actually I should have this so that the sum of it equals it. It should go like this, actually. This is kinetic energy. So that this, at any given point, this potential energy plus that kinetic energy added together would have to equal the total energy. Okay. Notice it's at a maximum when the potential energy is 0, and it's at a minimum when the kinetic energy is at a minimum as we go to 0 at these points where it hits. At these points called where the energies intersects the potential energy. Does that make sense? To some extent, maybe. This may be pretty rough. But what I'd like to indicate is there's a lot of other systems out there where you have potential energies and you can treat the total energy as kinetic energy plus potential energy. And in fact, if I drew any potential energy graph, something like this, around each of these points here, I can approximate that as a little parabola, just like this parabola here. And I can pretend that this is a mass on a spring, because it has the same shape of potential energy as a spring, right near the minimum of any potential energy graph. So this is actually a very general, this mass on a spring becomes very, very general in dealing with any type of potential energy, because near any minimum of potential energy, the potential energy graph looks like a parabola, and it behaves like a mass on it, and the system will behave like a mass on a spring. So that's kind of where I'm going to go with this right now, because one of the most common examples of simple harmonic motion is the pendulum. Let's say I have a pendulum with a bob of mass m hanging down here, an angle here like this. Turns out that this pendulum has a minimum of potential energy, where the gravitational potential energy is the greatest, is the lowest, when it's at its equilibrium position here, right? And even though the potential energy looks like 1 minus the potential energy for a pendulum would be L minus L cosine of that angle, which doesn't look like 1/2 kx squared. If I were to plot this, it would look something like this. As a function of angle. It turns out I can treat this similarly to a mass on a spring. And so the idea is, for a small angle near the equilibrium position, the pendulum behaves like a simple harmonic motion. The only difference is that omega is square root of G over L instead of square root of K over M. Where L is the mass of the pendulum, or L is the length of the pendulum, G is the acceleration due to gravity. So, that's the only difference between a pendulum and the mass on the spring is this omega. Other than that, it does the simple harmonic motion. One thing to notice is that this is independent of the mass of the bob. So for a pendulum, it doesn't matter how big the mass of the bob is, it'll all have the same period of motion. And also, it depends on the length of the pendulum, 1 over the length, square root of the length. So just to make sure that we got this all, a working knowledge of all of this, we can put this together a little bit. Give you one problem, and then we'll go over the test. If you want a pendulum with a period of 2 seconds, how long would you make this string? How long would you make this string? I'll let you get that really quick, okay? Take a minute, see if you can get that.
No, that's late. That's the one.